All right. The first thing I wanted to mention is that the next homework assignment, homework number 4, is available now. And let me just briefly show you what that looks like. There's 2 problems. So maybe that's a red flag already. It must be hard problems if there's only 2 of them, right? And the answer is yeah, kind of. So you've got a week to do 2 problems. The first problem you'll be able to finish after today's class meeting. We'll have the concepts covered that play into this question, and in addition to that, I'm telling you the step-by-step on how to solve it, because we're going to be doing a flow problem with 2 parallel pipes, and this problem has 3 parallel pipes. The concept's the same, but there are some differences, and so I've given you the step-by-step. On the second homework problem, we're going to start talking about the ideas that you use to solve this problem today. But it looks like a problem that it maybe looks like a Hardy-Cross problem, and next week we'll start talking about Hardy-Cross, but I say here in the instructions this is not a Hardy-Cross problem. Just to clarify, don't use that other method that we're going to learn later this week. So the main thing I just wanted to emphasize is please read all of these instructions before you start your calculations. So I've gone to the trouble of writing some tips here that over the last few years as I've been giving the same problem, I think that these tips will help out a lot. And occasionally I get questions that make it clear the students didn't read the tips yet. So I really think that it'll save you and me both a lot of time if you read through all of those comments that I've given you in the problem before you actually start your calculations. All right, so that's available now. It's due next week. And what we're going to be talking about today, this flow through parallel pipes, starts in section 8.5.2 of the textbook. So it's called the Nodal Method. And it's important stuff. So please, if you're not already in the habit of checking to see what the book is saying on the subject, this might be an especially good time to start, because I'll explain it the best I can, but we've only got 50 minutes to go through these examples, and sometimes that's not enough time to cover both the theory, the fundamentals, and the application in as much depth as you can get if you also follow that up by reading through the textbook. So section 8.5.2. All right, so you remember that we've looked at the Moody diagram before, and that the implication of fully turbulent flow is it's that region of the Moody diagram that's to the right of this dashed line where F value no longer is changing as the Reynolds number increases further. So that's fully turbulent flows. It means that flow is going so fast that the F value only depends on the relative roughness and not on any further increases of Reynolds number. So the way that you determine the F value when you're making that assumption is that if you use the Jane equation, you can cancel out the right-hand side term inside of the denominator, because you're assuming Reynolds number is big, and if Reynolds number is very, very large, that means that this expression is small relative to the case of S to D. So it simplifies the Jane equation when you make that fully turbulent flow assumption. Now, why would you make the fully turbulent flow assumption? Well, you'd make that assumption when you don't know what the velocity actually is, because Reynolds number depends on velocity. So the first time you're starting an iteration, if you don't know what's the velocity, then just kind of as a reasonable starting point, you can invoke this assumption and estimate F first time around just by the relative roughness. And then later on down the line, you're going to have to check it and see if there's an updated F value once you do have the velocity you need to calculate Reynolds number. In the same way that the Jane equation can be simplified, so can the Colebrook equation. Just that right-hand term, if Reynolds number is big, drops out. So you can also estimate the F value according to the Colebrook equation, if you prefer, through that fully turbulent. But in both cases, you need to later on check the assumption to see if it's valid. Now, the nodal method that we're applying today is just an application of the continuity principle. And last semester in fluid mechanics in chapter 5, continuity told us that what flows into a junction must go out of a junction. So here we have two pipes coming together. There's pipe X and Y that join together, and pipe Z comes out of there. So if you do a control surface that the flow is going in and out of, and we're going to say that here inside the control volume there's no capacity for storage. So we don't have a tank inside that control volume. We just have pipes going in and out. And if the pipes are full of water, there's no potential for storage. And so the flow rate out, QZ, is the flow in. So flow in equals flow out. That's continuity. We know it is continuity, and we're going to use that approach to determine the flow when the water could go through either of two pipes. So the application is, what if the water is flowing through a pipe and then it reaches a junction and it can go through pipe B, or it could go through pipe C. And then it may come back together again, but we don't know the distribution of how much is going through either of these. This is a top view, so it's not like a gravity thing. It doesn't have to do with which pipe is above the other one. It's not going to be related to that. Even if it was a side view, it still wouldn't have anything to do with gravity. But we will talk about what determines how much goes through one pipe versus how much goes through the other. What we know is that the flow that's going through this pipe B is the flow A minus however much is going through C. So this expression here for Q sub B is just simply saying the amount that's going through B is the total amount minus how much is going through C. I mean, that's obvious, right? If it's not going through C, then it has to be going through B. And then when it comes back together again, it's that known amount that we knew at the beginning. And so likewise for pipe C. However much is going through C is the amount that's not going through pipe B. Let's think in physical terms, like what this maybe is analogous to. And a couple of years ago, I went to Winter Place for the first time. I wish I was going there tonight, because my guess is they probably have pretty good snow, and we're supposed to get blasted, I think. I grew up skiing out in Utah, and so we had pretty good resorts there as well. And one of the ways that I like to think about this nodal method is in terms of the energy at the beginning and the energy at the end. So junction and junction. There's two different paths to get from the first junction to the second junction. You could go through pipe B, or you could go through pipe C. So now think about that. How does it relate to Winter Place? So if you go to the top of the mountain up here, there's several different routes you can go through to get to the mountain house. You could go down through Nosedive if you're feeling ambitious. It's a black diamond run, so that just means it's steep, right? But the elevation difference between the top of the mountain and the mountain house is the same if you go through Nosedive or if you go the scenic route. If you go via Woods Run, that's only a blue run here. The blue square means it's not quite as steep, and that's because it's a greater length. So the L is larger, but the elevation difference is the same. So the reason I showed you this picture is because, number one, I wish I was skiing today, but number two, also because it actually plays into this idea of different paths to get to the same destination. And really, you lose the same amount of energy regardless of the route that you take. So if your energy is the elevation and you're standing at the top of the mountain, you're not moving, so you don't have any kinetic energy. You've just got potential energy, your elevation. And when you get to the bottom of the run and you stop, you no longer have kinetic energy, you're stopped, then your elevation is how much potential energy you have. And so the elevation difference between the top and the bottom of the run represents how much energy was exerted to get there. And it doesn't matter whether you went woods run or nosedive, you've got the same energy change. So how does that relate to pipe flow? Well, let's think about these two different pipes, B and C. What if? What if they're both the same length, and they're both the same diameter, and they're both made out of the same material, meaning that they have the same roughness? Then how much of the flow would go through one versus go through the other pipe? Any guess about that? If they're identical in every way, what distribution would go, how much would go through B versus how much would go through C? Do you know which pipe would carry more flow? Logan says equal. Gavin says half and half. Andrew says 50-50 split. David Ball says 50-50. Exactly right. There wouldn't be any reason for more flow to go through pipe B versus C. You know, like if they have the same characteristics, there's no reason for there to be more flow going through one versus the other. So it'd be the same. All right, now what about this though? They're both the same diameter, they're both the same length, but pipe B is a rough pipe. Now maybe it's made out of concrete, whereas pipe C is made out of brass. So now, which of the pipes would carry more flow? The rough one or the smooth one? Less rough, more flow. Harrison says the smooth one carries more. Jacob says the smooth one. Exactly right. Now that doesn't mean it carries all of the flow. I mean, that wouldn't make sense either, right? If all of the water went through the brass pipe, no. Some of it will still go through the rough pipe, but there's relatively more flow going through the pipe that has less resistance. Okay, so I think what you're starting to see is that there are parameters that affect how much flow goes through each of them. And this formula for head loss is going to be the analogy between the ski resort, you know, the starting energy and the ending energy. So at this first junction, you've got a certain amount of energy. At the ending junction, you've got however much energy there was at the first one minus the losses through the pipe. Okay, so with this example we just did, where we said one of them was a rough pipe and one was smooth, there's energy at the first junction, and then you're losing energy as you go through the pipe, and then you get to a certain amount of energy downstream. And how much? Well, you just calculate the losses with this Darcy-Weisbach equation. And the same amount of loss occurs through pipe C. Even though it's a different flow rate, the same amount of loss occurs, because you can't end up at a different energy level. Just like here, it would be impossible to go down Woods Run, get to the mountain house, and be at a different elevation as somebody who had gone through nosedive. I mean, by definition, you're ending up at the same location. You've got the same elevation. Even though the nosedive person went faster and went maybe arrived more quickly, the elevation change or the energy loss is the same. So same thing here. Regardless of which route you take, the head loss is the same. Okay, so that's a big idea. Let's think about another real-world kind of illustration. What if it's the same pipe material, the same length, but now the pipe C has a larger diameter. Pipe B is a smaller diameter. So which of the two pipes is going to have more flow? C, good. Everyone agrees. It's pipe C is going to have more flow because larger cross-sectional area, relatively more water can flow through there with less resistance because more of the cross-sectional area is farther away from those edge boundaries where the shear force is applied by the pipe to the water. So as the water flows through the pipe is resisting that movement, and if you've got a big diameter pipe, the center of the pipe is pretty far from where the resistance is applied. So more flow is going to go through pipe C than goes through pipe B. Okay, now what about this one? All right, so the diameter of pipe B is bigger. So So that would mean maybe pipe B gets more flow. But the length of pipe B is longer. Well, that would mean it's going to get less flow. And now pipe C is more rough, whereas pipe B would be relatively smooth. Now what's going to be the flow distribution? Well, we don't necessarily know just from these inequalities that are described. We need to know magnitudes at this point. And so at this point what we'd have to do is get the specific numbers and put them into the head loss expression to find out which of the flow is going through there. So we don't know just by inspection with this one. We can do calculations, but the general principle is that the head loss through both pipes is the same. So think about what this means. You've got some energy at the junction. When the pipe comes back together again, you've got the same amount of energy once you come out of the pipe. So that must mean that the head loss is the same through each of them. Okay, so the head loss through each flow path is equal. So what that means is this is the formula you can use to calculate the relative velocity through each pipe. So we've just simply used the Darcy-Weisbach equation for pipe B, and that's equal to the head loss through pipe C. And so if you know the numerical quantity for the friction factors and the lengths and the diameters, you can find the velocity of one pipe in terms of the velocity through the other pipe. So this by itself is only one equation, but our other equation that we is continuity. Is that considering that they have equal Q? No, that's a good question, Gavin. This is true even if they have different flow rates going through each pipe. But what we combine this with is we combine this with continuity at the junction. So we know that QB plus QC is equal to QA. So that's going to be kind of the other piece of the puzzle. So we don't assume that QB and QC are equal. In fact, it's going to be rare that the flow rates would be equal. All right, well, let's try this out with some real numbers. But just to summarize, what it means is it doesn't matter how you get from 1 to 2. It doesn't matter if you go through pipe B or through pipe C, but the head loss is the same through either route. It has to be. You couldn't end up at 2 with a different amount of energy because you're at the same location. You have to have the same amount of energy. Speaking of energy, what does the energy equation look like? Have you used it enough times that you could write it by memory? Z1 plus V1 divided by V1 squared divided by 2, pressure head, that whole thing. So here's the energy equation. On the next slide, I'm going to show you a different way of writing the energy equation. It's still this. When I say energy equation, it's still these same ideas. We're going to rearrange, we're going to write it a little bit differently. And when I do, I'm going to write it in terms of head. At 1, the total amount of head at 1 is the pressure head, elevation head, and velocity head. And so H1 is those three terms combined. And H2 is pressure head at 2, elevation head at 2, and velocity head at 2. So don't be freaked out in just a second when I show you this formula. Nobody's freaked out, right? Everyone's calm because it's the same thing. It's still this equation. We just wrote it differently. So this is just solving for the head at 2. When you know how much energy or head there is at 1, minus the losses between 1 and 2. So this minus term is saying minus the frictional losses, minus the local losses, and in both of those cases we have to multiply it by the velocity head. Wait a minute. This isn't velocity head, is it? Yeah, this is just velocity head. Q times Q divided by 2G A squared. That's the same thing as V squared divided by 2G. It's just that later on it'll be useful for us if we have this equation, instead of having it in terms of velocity, if we have the velocity head in terms of flow rate, it'll be simpler because we will know the flow rate in some cases, but we don't know the velocity through the pipe. Like for instance, if we have different pipes and we're splitting the flow. And then the absolute value is useful because sometimes in a pipe network you don't know if the water is going one direction or the other. Like going back to the homework, let me show you that homework problem, this one. We don't know if the water is going from A towards C, or maybe the flow is going from C towards A. So we don't always know the flow direction in some networks, and having the formula written this way with an absolute value of Q allows us to have a convention for flow direction. And then if our calculations end up wrong, then we can change the flow direction. So I'm just kind of explaining the background for why we're keeping track of the absolute value of Q. Or you may even be looking at the pump head term and saying, well, why even have flow rate in here if it's going to be canceling itself out? And it's because flow direction is a factor. All right, so this equation is just the energy equation. It's saying the amount of head at 2 is how much head you had at 1 minus the losses. Now between 1 and 2 in this diagram there's no pump, so forget about that last term. Between 1 and 2 there's just friction losses and local losses, and sometimes there may not be local losses. It could be that there's only friction losses. But the main idea here is that water flows from upstream to downstream, and so our convention is that we say location 1 is the upstream location and location 2 is the downstream location. So the water's going from 1 towards 2. Okay. So here's all of our definitions of the terms. Big whoop. We already saw it. It's just the energy equation. All right. The water flows from 1 to 2. Now, here is where we start to make it interesting with some real numbers. Let's say that there's 3 cubic meters per second going through pipe A, and then when the 2 pipes join back together again, it's that same 3 cubic meters per second. There weren't any laterals drawing off flow. It's just, it's split temporarily. And we want to know how much is going through each pipe. So the first thing that we could do is, if we know the elevation and the pressure and the velocity of the flow, we could calculate the total head at 1. And then we could also determine the total head at 2 by subtracting out the losses through one of the pipes. But even if we don't know the pressure at 1, we could still find out how much flow is going through B versus how much is going through C, just by knowing the characteristics of the pipe, like its length and diameter and friction factor and so on. But the head at 2 is going to be how much head there was at 1 minus the losses. And if there was a pump in between, then there could be gains as well. So here's what we're going to do. We do know some stuff about this location. We know that there's 3 cubic meters per second going through pipe AB, and the diagram tells us what was the pressure at A, and then there's pipe 1 connects A to B, and so we know the length of pipe 1, its diameter. I've already gone ahead and calculated the flow velocity and F value just to speed things up a little bit. But what we don't know is we don't know how much goes through pipe 2 versus how much goes through pipe 3. Let's see if you could guess. Let's see if it's going to be an obvious one. Because sometimes just by inspection we can know which is going to carry more flow. Anybody have a guess for which of the 2 pipes, pipe 2 or pipe 3, which one is going to have more flow going through it in this system? Everybody's saying pipe 2, and that's exactly right. Anybody want to explain why pipe 2 will carry more flow? How is it that in this case it's definitive that pipe 2 is going to have more capacity? What are the characteristics that revealed that to you? Larger diameter in pipe 2, and then also the length is less. So it's not just about the length. So pipe 2 is shorter, and a shorter pipe will have less resistance. A larger diameter pipe will have less resistance. We don't know the F values, but we do know that all of these pipes are galvanized iron. So the resistance will be, I think the resistance will be less through pipe 2 because it's a larger diameter. So that's just another reason why there's going to be more flow going through pipe 2. Okay, so here's what we're going to do. I'm going to pause from talking for a second, and I'd like you to start with the area that's given. We don't know the velocity yet. We will. But since you don't know the velocity, you couldn't use the full version of the Jane equation. So invoke the fully turbulent flow assumption. Here's the simplified Jane equation with no Reynolds number term. So assume if it's fully turbulent, what is the F value for pipe 2 and what is the F value for pipe 3? And then use that, substitute everything in to this equation to find what is the velocity of 2 in terms of the velocity of 3. Okay, so I'm going to pause and you're going to calculate F for pipe 2, F for pipe 3, and then find out V2 versus V3. And if you want, you can take it all the way through to finding out what's the actual flow rate by doing the continuity at junction B. But let's just first start by calculating the F values and then the relative velocities. I'll put you into the breakout rooms because that's been working okay, I think, recently. We haven't had any audio issues. So let me shove you into the breakout rooms, and that way you can check your answers and discuss breakout rooms just when you were getting comfortable. All right, so let's take a look at the calculations for the F values. I think I have the calculations I can just drag over, and we'll take a look at it together. Yes. That's a little crooked. All right, so we've got pipe 2 and pipe 3. And our governing idea that we're going to be applying is that the head loss through either route is the same. But before we get to that, if we apply the fully turbulent flow assumption, meaning that we're just going to neglect any effect of a high Reynolds number, so then that means the F value for pipe 2 is 0.01493, and then pipe 3 has an F value of 0.01567. So pipe 2 has less resistance than pipe 3, in part because the diameter is larger. Now, since the head loss is the same through either route, the implication of that is that we set the two Darcy-Weisbach equations equal to each other. And we can rearrange to get V2 in terms of V3. So that's what I've done, is I've algebraically rearranged that equation so that I'm going to have V2 in terms of V3. And you could have done the reverse of that. It would also be okay to find V3 in terms of V2. But you'll see that I canceled out the like terms of 2G, which is both in the numerator and in the denominator, and then the substitutions that I've made here with the diameter of the pipes, the F values of the pipes, and the lengths. And then I have to make sure that I get that square root term because I'm finding V2. So I say that V2 is 1.204 times V3. So that just tells me that there is a faster velocity in pipe 2. So pipe 2 has a faster velocity, and also pipe 2 has a larger diameter. So pipe 2 is definitely carrying more flow. If it has both a larger diameter and a faster velocity, more flow is definitely going through pipe 2 because there's less resistance. But it's not all of the flow is going through pipe 2, just more of the flow is going through pipe 2. All right, so now we add the continuity relationship that combined together, pipe 2 and pipe 3 are carrying 3 cubic meters per second. So A2V2 plus R2D2, no, that's too funny. A3V3 is 3 cubic meters per second. And we substitute in the known cross-sectional area, and then we're writing, instead of V2, we're writing it in terms of V3. And then that way we're only going to have one unknown in this equation. You know, because we had 2 equations, 2 unknowns. So when we combine them together, now we are solving an equation with only one unknown. So it's going to all be in terms of an unknown V3. So the velocity through pipe 3 should be 8.29 meters per second once we substitute it into continuity. And then from that, we know what the velocity through pipe 2 is, because it's 1.204 times as large. All right, so we know the velocity through each pipe, and therefore we can find the flow rate through each pipe. And of the 3 cubic meters per second, 1.04 goes through pipe 3, 1.96 goes through pipe 2. So pipe 2 is carrying almost double. Any questions so far about these ideas? I mean, it's one thing if maybe you had a calculation mistake along the way. It's easy to type the wrong numbers into your calculator. But the main thing that I hope you're taking away from this example is the idea that it doesn't matter which pipe you go through, the head loss is the same through either route. That's the big idea here that we're using to solve problems. And so we use the fully turbulent flow assumption, and sometimes that'll be a valid assumption, sometimes it's not a valid assumption. And if it's not, what it means is we need to do all this over again and calculate the relative velocities with an updated F value. So we always kind of got our fingers crossed that that turns out to be a valid assumption. And how valid? Well, if the F value is within a couple of percent, then that's close enough. So now that we have an estimate of the flow rates, let's check the fully turbulent flow assumption. We need to check the validity of the fully turbulent flow. Before I move on, is there any questions? Okay, so this is where we are double checking to make sure that fully turbulent flow isn't too simplistic. So we use the 2 flow rates that we've just determined to find the Reynolds number through each pipe. So the Reynolds number through pipe 2 is about 5 times 10 to the 6th. Reynolds number through pipe 3 is 3.3 times 10 to the 6th. Now, we'll calculate the F values for each pipe with the full version of the Jane equation this time. So we're not just doing the abbreviated version of the Jane equation. So with the full version of the Jane equation, it turns out that pipe 2, the updated F value is 0.01498. Well, what was it originally? 0.01493. That's pretty close. That's within 1%. So we breathe a sigh of relief. We don't have to redo this, and the same thing is true with pipe 3. 0.0159 versus 0.01567. So again, 1%, we're good. Fully turbulent flow assumption is valid, and these flow rates that we'd calculated before are the flow rates through each pipe. But if it had been that maybe we got a pretty significantly different F value, then what that would mean is that now you take this F value and that one and redo at this point. So we would just put in, I mean, I guess it wouldn't be the end of the world, right? We've already set everything up. We just put in the updated F value there, the updated F value there, and we'd get a slightly different ratio of velocity 2 in terms of velocity 3. And so, I mean, it would subtly update the distribution of flow through each of those two pipes. That's the process for the nodal method. Any questions about that? Regarding the homework, you've got flow going through 3 routes instead of 2. The same principle applies though. You've got a certain amount of head at A and a certain amount of head at B, and the head loss through pipe 1 is equal to the head loss through pipe 2, and that's equal to the head loss through pipe 3. So all of the head losses are equal. So you could say that, you know, when we had this equality relationship in the solution, this one, F2, L2, V2, we could also have that be equal to F1, L1, V1 on the homework. Here. So the head loss relationships are going to be that the head loss is the same through any of the routes, and we are knowing that the combined flow rate is 0.3 cubic feet per second. And so I'm kind of giving you the step-by-step here. First, use an initial guess for each pipe based on fully turbulent flow. Write the V1 and V2 in terms of each other. Now write an expression of 1 in terms of 3. Then substitute it all into the continuity equation. So, I don't know. I feel like maybe I gave you too many hints on this one. But I don't always do it that way. I certainly didn't give you too many hints on problem 2. I gave you just the right amount of hints on problem 2. Any questions about this nodal method? All right, well, that's all I have for you today, and it works out great because we're out of time. Remember that the next assignment is due on Wednesday, so you've got a week for that one. You could already finish the first problem if you're an early bird. That's great. And check out your book. It's pretty good. There are a lot of bad hydraulics books that we're not using this semester. We're using the good one. So I hope that you take advantage of the clear explanations that are in there. If you've got any questions, feel free to send me an email or call me on Teams. I'd love to hear from you. Have a good day, and I will see you on Friday.